Hey, and welcome back to Integrated Science. I'm Miss Sparks, and today we're going to be talking about acceleration, which is a continuation of our motion concept and starting to talk about how motion is going to, we're leading up to pretty much how is this going to be in play with Newton's three laws of motion and how force is going to be a portion of this. So we kind of talked about that last with things here on Earth obviously have gravitational pulls. Things actually out in space have gravitational pulls too, and we'll talk about those differences here as we kind of move through. But an acceleration is the continuation of understanding how we can solve for speed with using our equations, distance over time. Let me grab my board from when we talked about this. So once again, we have our T-charts there. T-charts, and then our equations for speed and velocity. Speed is, once again, distance divided by time. That's a scalar model. We are finding the magnitude of that. And velocity is the same, distance divided by time. However, in that one, we are going to provide a vector, which is going to give us a direction. Now, acceleration is going to be a combination of speed and velocity, and we're going to add to it a little bit. So once again, you're going to want to get out a sheet of paper to take some notes. I will be introducing an equation on how to find acceleration, and then we'll be looking at some simulations and how we can actually model and look at how objects can have a positive and or a negative acceleration. And once again, this all goes with our quantitative data, meaning that we can give a quantifiable measurement for acceleration, just like we did previously with speed and velocity. So let me go ahead and get us moving here. All right, so the definition, the formal definition for acceleration is just the process in which velocity changes over time. So we're looking at that change. And sometimes in science, you'll see that referred to as a triangle. Oh, this blue does not look good on this gray. Let me erase that. Perfect. And get some little bit of a different color, something more soothing on the eyes. I think this blue will be better. Oh yeah, that's much better. There we go. So velocity is a change over time. And so sometimes you'll see it written as a delta symbol, which is the Greek symbol of a triangle, which means change. We want to see what is the change that is occurring there. And so we are looking at object's acceleration if speed, direction, or both change. So there's a couple pieces of information. If speed changes, then acceleration has changed. If direction has changed, then acceleration has occurred, or if both. I always like to think of this as a little clip in the movie Cars with Lightning McQueen and Mater. This would be the first one where they're at Radiator Springs and Lightning's already messed up the road and he tried to pave it and he did it real fast and it made it all wobbly and bumpy, and Mater was going down like, oh, this feels great. Technically it wasn't. So then Doc said, this isn't going to work, you need to redo it, and somehow they got into an argument, and Lightning challenged Doc in a race around the track. And so let's set the scene. So they're all at the track, and remember, this is a dirt track at Radiator Springs, and I think it's Luigi with his little flags, just like 3, 2, 1, and Lightning speeds off, goes super fast down this dirt path, and Doc just sits there. And hopefully you've seen it. If not, go back and look at it. This will be one of many ways I try to connect Disney to science here, so just bear with me. So anyway, Lightning McQueen goes down the track, going really, really fast because he's ka-chow really fast, and he hits that turn, and as he's changing his direction, he doesn't compensate for being on a dirt road versus a asphalt one. So the friction and the gravity that is all kind of happening there in the physics causes him to go off the side of the road and into the ditch, and then Mater has to pull him out, and then he still has to pave the road, and everyone loves Radiator Falls after that. So, but the idea behind that is that Lightning McQueen changed his speed as he was going through there, and he changed his direction during that turn, but he didn't change his speed, so it caused him to drift off the road. So you have to make compensations as we are moving through different types of scenarios, and that's what this is talking about. Acceleration can happen. It could be speeding up. It can be slowing down. It could be changing direction. It could be changing direction all the time. So think about, once again, the Earth orbiting around the sun. We're constantly changing our direction, so it's constantly technically accelerating, or if it's doing both. And so if it's speeding up and changing its direction, then it could be acceleration too. Or it could be slowing down and changing its direction, and that would be acceleration too. So these all three play a very big part on each other. And once again, you'll see this delta symbol kind of pop up here and there as we kind of move through a couple of different activities through the next couple of days. So acceleration is just that. So kind of just what I talked about here is if an object is increasing its speed, if it's going faster and faster, we call that a positive acceleration. So if you think about our little line graphs, that would just mean that we would have an increasing acceleration, and we would have our time down here on our X, and on our Y, we're now going to have our speed. I'm just going to draw it as an S. And then if it is an object that is slowing down, then we have what is called a negative acceleration. Go ahead and label these two so that I'm accurate. T and S. So when an object is slowing down, then we have a decrease, and it's just a negative acceleration. It's slowing down. So sometimes we can have numbers that will start to pop up that have a negative sign in them, just depending on how we're going to set it up in the equation. And so therefore that's going to tell us, is that a positive? Is it speeding up? Or is it a negative? Is it slowing down? And then we'll be able to graph them out and do all kinds of other quantifiable measurements with them. So very fun, exciting stuff. We're moving into some stuff that actually I feel like really kind of gives us some tangible information. So changing direction is kind of one of the other things that we talked about earlier on that first slide, in which can cause an object to accelerate. So anytime a moving object changes its direction, it has to compensate for that speed and that friction, and so it changes its acceleration too. So think about like riding your bike or a skateboard or roller skates or rollerblades or anything. If you're going really fast and then you have to make a turn, you probably don't want to make that turn in that same speed. You might have to slow up a little bit, just because you don't want to lose friction and then tumble off into the ditch like Lightning McQueen. So changing that direction will cause for velocity to speed up or slow down. Most of the times it could be either or, but I feel like here on Earth it helps if you slow down just a little bit so that you don't end up tumbling over. So our equation for acceleration. So to calculate acceleration, there's a couple of pieces of information that we're going to be looking at. And once again, it piggybacks off of what we used previously, which is velocity. So here's our equation down here, which is acceleration equals the final velocity of an object minus the initial velocity of an object and how long it took to do that. Most of the times you'll see me write it like this, which is A equals VF, F stands for final velocity, minus VI. This is the change. This is that triangle I was talking about, that delta, the change in velocity over the change in time. You kind of want to think about it that way. So final velocity minus initial velocity and the time that it took to do that. So I'm going to write one more equation over here on my whiteboard so that we can kind of look at some of these a little bit too. So T-chart as well, it just becomes slightly more complicated because we're adding another variable in there. And let me just write the equation out for you. So once again, these are, oops, that is what we're looking at, our peek around here on the corner. Our final velocity minus our initial velocity over time. So we're going to use that equation quite a bit. So let's look at one. So suppose a jetliner starts at rest and ends at the end of a speedway and reaches a speed of 80 meters per second in 20 seconds. So what is its acceleration? So that's what we're solving for. So I'm going to go ahead and draw my little t-chart over here. Our final velocity, that's a terrible V. Wow, that's bad. BI and our time. This is terrible. I should just write it on the whiteboard. I can't even draw a straight line there. And let's look at our equation once again. Let's just have it up here for us. Our final velocity minus initial velocity over how long it took to do that. So let's look at our word problem again. So we know it's asking for acceleration. So that's our unknown. That's our variable there. And then once again it says suppose a jetliner starts at rest at the end of a speedway and reaches a speed of 80 meters per second in 20 seconds. So there's some pieces of information. Let's go in and fill what we know. 20 seconds is easy. We should know that that's our time. Our 20 seconds goes here. There's that mysterious line that loves to pop up. I'm not even going to try to erase it at this point. Yes, I am, because you know it will drive me nuts. And it took away my 2. There it is. All right. We also have this 80 meters per second. There's a couple of pieces of information we kind of need to read into this equation, though. It says reaches a speed. So if it reaches a speed, is that its initial velocity or its final velocity? And technically, if it's reaching that, it's going to be its final velocity. So we're at 80 meters. Oh my goodness. Guys, technology and me, I try really hard, but technology always seems to make me feel I need to know more. All right, so meters per second. And there's, what do we do here? There's no more numbers. So we have to look at what the text is actually saying to find our initial velocity, and it's right up here. The jetliner starts at rest, So it's at a stopping point. So it doesn't have a speed at all. So that's going to be 0 meters per second. And all we're going to do now is plug them into our equation. So A is now our variable of our x, our unknown. And we know the final velocity is 80 meters. Per second. And we know the initial velocity is 0. And how long did it take to travel that? 20 seconds. All right, so now we've got it set up correctly. We've got everything where it needs to be. And now we just need to simplify. So 80 minus 0 is still 80 meters per second. And we're going to divide that by the 20 seconds of time. And when you type that into your calculator, you should get well, where is my calculator? I can't find it. Well, it would be 4, right? It should be. If I can do math in my head, which I should be able to. I can, still can. So 4, sorry, I don't know what I was looking for there. Meters per a second. So that's our final answer, 4 meters per second. Let's look at a graph here. Oh, here's another one. A bike rider moves from 0 to 25 meters in 10 seconds. What is its acceleration? So take a minute. I want you to set this up into the T-chart and then solve.